Welcome to The Explainer. Okay, today we're jumping right into a story that literally bridges a tiny, picturesque Italian town to a massive global maker revolution. We're talking about a journey of open-source innovation, creative problem-solving, and taking incredibly complex technology and making it accessible to absolutely everyone.
Because really, think about it. How exactly does a tiny circuit board, named after a local pub of all things, end up sparking a global scientific revolution? It's just an incredible trajectory for a piece of open-source hardware that only costs about 30 bucks. We're going to trace that exact journey today, exploring how a simple tool meant for design students ended up powering complex laboratory equipment all over the world.
It's all about access. Look at this quote from co-founder Massimo Bonzi. He hit the nail on the head when he said, 50 years ago, to write software you needed people in white aprons who knew everything about vacuum tubes. Now, even my mom can program. He viewed this project as the absolute democratization of engineering.
Section 1. The birth of Arduino. So let's travel back to 2005 at the Interaction Design Institute Ivrea in northern Italy. Take a look at these humble, almost meatball surgery beginnings. Exposed wiring, super basic components. It's a true DIY prototype. But here's my favorite part, the name. The founders actually used to hang out at a local watering hole called Bar the Re Arduino, which was named after an 11th century Italian king. Over drinks one night, they're like, let's just name our invention after the pub, and it stuck.
Section 2. Democratizing DIY electronics.
Picture the early 2000s. Design students need to learn electronics fast to build interactive prototypes, but the barriers to entry were massive. The standard back then was the basic stamp. It ran you about $100, had a brutal learning curve, and get this, it wasn't even Mac compatible, which was a huge problem for design students. Then comes Arduino, a $30 board, basically the price of a pizza dinner, equipped with easy-to-use open-source software and simple plug-and-play USB capability. A real game changer.
When mass production ramped up, the team did something truly wild for the hardware world. They used a Creative Commons license, the thing usually reserved for cultural works like music and art. They used it to make the hardware completely open source. Anyone could look under the hood. Plus, they threw in these quirky design choices, like making the board blue instead of the boring standard green and stamping a little map of Italy on the back. And despite this totally unconventional DIY approach, they kept the failure rate under 1%. Absolutely wild.
Section 3. Meet the Mega 2560.
Okay, let's zoom in on the hardware itself. This is the Arduino Mega 2560 R3. It's the much larger, beefier sibling to the original boards. Right in the center, you've got the ATmega 2560 microcontroller chip. That's the brains of the whole operation. Over on the left is that silver USB connection for programming, the black power jack right below it, and a tiny reset button. You'd reach for this specific board when you're tackling really complex projects, stuff like 3D printers or robotics, where you just absolutely need more room to connect things.
Breaking down the specs, it runs on that ATmega 2560 chip with a 16 MHz clock speed. For memory, it's packing 256 kilobytes of flash memory to store your code, 8 kilobytes of SRAM, and 4 kilobytes of EEPROM. As for power, while it does have a wider limit, the recommended operating voltage is strictly 7 to 12 volts. You really want to stick to that range so you don't overheat the voltage regulator.
Section 4. Pins, power, and programming.
Now, what's really interesting here is the sheer complexity of this architecture. This central chip acts as the ultimate bridge. It takes raw stimuli from the physical world, analog data coming from light sensors, temperature sensors, whatever you hook up, and literally translates it into the digital world and vice versa. It's like a tiny, super-powered translator for your environment.
And to handle all that translation, the capacity here is massive. We're talking 54 digital input/output pins, including 15 dedicated to PWM output for controlling things like motor speed. Throw in 16 analog input pins and 4 hardware UARTs for serial communication, and you've got yourself an incredible amount of room for complex wiring. You are not going to run out of connections anytime soon. But with all that DI wiring power, you've got to have protection, right? The Mega 2560 has this brilliant built-in failsafe, a resettable polyfuse. Basically, if a short circuit happens and more than 500 milliamps hit the USB port, this fuse automatically snaps the connection. It saves you from totally frying your computer's USB port while you're experimenting. A real lifesaver.
Section 5. Arduino in the lab.
I want to zoom out for a second and look at this number, 1,122. According to a recent massive bibliometric analysis,
That is the exact number of published documents in the Scopus database focused completely on using Arduino boards in real scientific applications. It's absolute proof that this is no longer just a weekend hobbyist toy.
Tracing that timeline is wild. You start in 2005 when the platform makes its humble debut in Italy. Just 3 years later, in 2008, the very first science conference papers using Arduino start popping up in the literature. Fast forward to 2022, which was the cutoff for this particular study, and we're seeing an explosive, exponential growth in how it's being integrated into serious, rigorous scientific research.
Section 6. The Maker Revolution.
So, what does this actually look like today? Researchers are aggressively deploying these boards across biology, chemistry, and physics. It's empowering scientists to build their own custom, low-budget lab equipment. They're creating advanced IoT networks, deploying real-time monitoring devices, and building fully automated data acquisition systems. It is completely disrupting those traditional, highly expensive laboratory setups.
Which leads us to a pretty exciting final thought for this explainer. Think about it. If a $30 open-source board named after a pub could literally democratize both engineering and global science, what could you build with one today? The tools to create, measure, and innovate are quite literally in your hands. Thanks for exploring this fascinating topic with me, and keep learning.